Next, we will consider one more theorem. It is basically a necessary and sufficient condition for an estimator to be UMBUE. So what I am writing, is it clear? Is it visible?
Yes, sir.
Yes, sir. So I will state it in the form of a theorem. So let us firstly consider, let UG, suppose I consider all estimators T such that expectation of T is equal to G theta. Okay, that means this is the class of unbiased estimators of G theta. So our problem is to consider the UMBU is of this parametric function. Okay. So if I take G to be 0, then what will be the class? Then U0 is the class of all unbiased estimators of 0. Okay. So this necessary and sufficient condition is obtained in terms of relationship with class UG and U0. Okay. So I'll put it in the form of following theorem. The estimator T, which is unbiased for G theta, and of course we will have to put a condition on the variance, because if it is, we are saying that the variance is minimum, then it should be a finite variance. So it has minimum variance at a point, say theta is equal to theta naught, if and only if covariance of T with, so I'll put another number, say S. Okay, if this is 0, for every S belonging to U0, with, of course, variance of S should also be finite. So this is a necessary and sufficient condition that an estimator is having minimum variance if and only if covariance of that estimator with an unbiased estimator of 0 is 0, and it is true for every unbiased estimator. So this is a powerful result. It is used actually for proving lot of distribution theory results regarding covariance and calculation of independence, etc. So let us look at a proof. Of course, proof is not very difficult. Let us consider, say, so T is an unbiased estimator of G theta, and variance of this I am assuming to be finite, and suppose it is having minimum variance. So variance of T at theta naught is minimum. Okay. Because we are proving the result at a local point, and if it is of course minimum variance unbiased estimator at every this one, then for all theta it will be true. So let us take another S, which is an unbiased estimator of 0, and let us take, say, covariance between T and S to be non-zero. Actually, we have to prove that it is 0, so we take it to be non-zero. So I define another term. Let us define, say, V is equal to T plus say alpha S. Okay, where alpha is a constant. Then what can I say about V? This is equal to expectation of T plus alpha times. So alpha is a real. Okay, expectation of S. Now expectation of S is 0 and expectation of T is G theta. So V is also, an element of, so we can just write like this, that V belongs to UG. Okay. Let us put a condition here. Variance of, say, V. Okay, this V and this V is different. So let me use a full notation here, variance. Okay. So that is variance of T plus alpha S, that is equal to variance of T plus alpha square variance of S plus twice alpha covariance between T and S. Okay. Let us put a condition here. That this is less than variance of T. Note here, I have assumed that variance of T is minimum, and I am now putting another estimator whose variance is smaller than variance of T. So I am putting a false statement. So I will just see whether this is a feasible statement or not, because if my assumption is true, then this cannot be true. Now let us see. So on both the sides I have this variance of T, so I can cancel it out, and this is equivalent to, I can take alpha common, then I will get alpha times variance of theta naught S plus twice covariance of T and S theta naught, that is less than 0. Let us put some name to this condition. So when this condition will be true, the product of two terms is there. So the condition is true if alpha lies between 0 and minus twice covariance of Ts divided by variance of S. In order that this is a valid statement, because variance is always positive, the numerator should become positive, isn't it? Because alpha is greater than 0, so the right hand side should be positive. So I should put the condition that covariance of T and S is less than 0. Okay, and if I take alpha to be negative, then this condition can be written in the reverse way, that is minus twice covariance Ts by variance of S less than alpha less than 0. This is if covariance of T and S is positive, because if I want to have the left hand side negative, then I should have covariance to be positive. So let us look at the sequence of assumptions that I made. I made the assumptions that variance of theta naught is minimum. And then I am considering another unbiased estimator of 0 whose covariance with t is not 0. If that is happening, then I am able to get another estimator which I am calling to be V, whose variance is less than the variance of theta naught, variance of t at the point theta naught for a given value of alpha. And since I am taking covariance to be non-zero, both these conditions are feasible. That means either it is negative, then also I can get a choice of alpha, and if covariance between t and s is positive, then also I am getting a choice of alpha, such that variance of t plus alpha s is less than variance of t, which is a contradiction. This contradicts the fact that covariance of t with s at the fact that variance of t at theta naught is minimum. Hence, this must be 0. Okay. So we cannot have the condition that covariance between t and another unbiased estimator of 0 is non-zero. Now let us look at the reverse part of it. Conversely, let us consider covariance of t with s to be 0 for all s which are unbiased estimators of 0. And let us consider another term. Let us call it, say, t1 be another unbiased estimator of g. Then if I define s is equal to t minus t1, then this will belong to u0, because expectation of s is expectation of t minus expectation of t1, that is 0, because both are unbiased for g theta. Then it is given that covariance of t and t minus t1 is 0. Now you expand this. This is nothing but variance of t minus covariance of t and t1, that is 0. That means you are saying variance of t is equal to covariance of t and t1. But by the correlation inequality, that the correlation lies between -1 to 1, this is always less than or equal to square root of variance of t and variance of t1. So if I have taken variance, this t to be the minimum variance unbiased estimator, then what is happening here? You are getting variance of theta naught. T is less than or equal to square root of that. You cancel out this on both the sides. This gives you variance of theta naught t is less than or equal to variance of t1 at theta naught. This proves that t is having minimum variance at theta naught. Okay, so is the proof clear to you? Is anybody having any doubt? Any questions? Is the proof clear to all of you?
Yes, sir.
Yes, sir.
Another thing which you note here, from this derivation which I have written here, in this derivation you see what I have written finally, covariance of T with T1 is equal to variance of T. Now variance is always a non-negative quantity, so that means covariance between a UMBUE and any other unbiased estimator of G theta, it will always be a positive quantity. Okay, so this is an additional statement that I should write here. Let me put this as some number here so that you can refer to that, this one. Now let me put it number 2. From relation 2, we conclude that the covariance and as a consequence correlation also of UMVUE of a parametric function G theta with any other unbiased estimator of G theta is always positive. Let me put it as several remarks, because this is one another comment also I can write here. So if I apply this theorem here and I am considering say 2 functions, so let us consider T1 be UMVUE of G theta and T2 be UMVUE of, so let me put here G1 theta, okay, and this is UMVUE of G2 theta. Then any linear combination of the UMVUEs remains UMVUE for the corresponding linear combination of the parametric functions. Because if I take the covariance between this and another unbiased estimator of 0, then that will become covariance of T1 with some S and covariance of T2 with S. Both will be 0, and therefore covariance of A1 T1 plus A2 T2 with S will also be 0. So this statement is also true. This is partly because of the linearity of the expectation also, because unbiasedness will be maintained. Okay. Later on, I will give you applications of this theorem. Right now, it looks like an abstract result, but in distribution theory, in order to obtain covariance or correlation between certain terms, this theorem is very useful. So I will give you applications of this when I tell you some methods for finding out the UMVUEs. Okay, but before that, let us consider discussion about the methods for finding out estimators. What you have done, you have learned the criteria for estimation. That means if there is an estimator, what are the desirable properties that it should have? So for example, unbiasedness is a desirable property, consistency is a desirable property, then having a smaller mean squared error is a desirable property. For unbiased estimators, having a minimum variance is the desirable property because it means efficient estimator. That means the precision of the estimator is good. Okay. But the question is that how do you derive? The exercises that I gave you for unbiasedness, consistency, etc. Mostly it is heuristics. For example, if I am estimating the population mean, I am taking the sample mean. If I am taking the population variance, then I am taking the sample variance. I also gave you the examples of distributions where the least value of the sample or the maximum value of the sample was used, and we constructed estimators based on that. But again, all of this is based on heuristics. That means you should have a well understood or well developed thought process from which you can actually derive those conclusions. But are there some proper methodologies where I can apply that method to derive the estimators? So fortunately, such things are there. So let me start with the methods. Okay. Methods for finding there are several methods, but I will discuss the ones which are more common and easy to implement, and they generally yield good estimators. The first method of this is called the method of movements. This was actually introduced by Karl Pearson, okay, around 1890. I mentioned to you in the beginning that Karl Pearson, R.A. Fisher, Georgi Neyman, and Pearson, they are considered as the initiators of the subject or the major ideas of the statistics, and the timeline is around 1900 to 1930. They developed most of these methods. So let us consider, say, x1, x2, xn, a random sample. So as I mentioned to you that we will use some sort of standard notation and terminology here. So generally I will use p theta as the distribution, because it may be discrete distribution, it may be continuous distribution. So you may have a PMF or PDF, etc. So I'll use a little more general setting from a probability distribution p theta, where theta is of course it can be one dimensional, two dimensional, and so on. So I'm just in general writing k dimensional. Okay. What is the basic problem here? The basic problem here is to estimate theta i's. Okay, theta 1, theta 2, theta k. For example, in a normal distribution, I would like to estimate mu and sigma square. In a Poisson distribution, I would like to estimate lambda. In a gamma distribution, I would like to estimate r and alpha, and so on. So our aim is to obtain estimates of theta 1, theta 2, theta k. So in method of moments, we consider first k non-central moments. Okay, non-central moments means the moments about the origin. That is mu1 prime. You remember in the course of probability and statistics, the notations mu1 prime, mu2 prime, and so on. Are you clear about that? Because I am straight away writing that. So if I want to calculate, say, expectation of x1, that is the first non-central moment or the mean of the distribution. So I'll call it mu1 prime. So it will be some function of theta 1, theta 2, theta k. Similarly, if I consider say expectation of x1 square, then that is some other function of, for example, if I am considering say binomial distribution, then the mean is np, second moment is npq plus n square p square, and so on. So I will write up to k terms, because if I am having k components of the parameter, I will write g1 theta, g2 theta, gk theta as mu1 prime, mu2 prime, mu k prime. Okay, is there any confusion about this notation? I think all of you must be familiar with this in your probability and statistics course. If anybody is having any doubt, you can consider these as some equations. As I mentioned, mu1 prime is np, mu2 prime is equal to npq plus n square p square. So these are some equations in theta 1, theta 2, theta k, because the left hand side can be evaluated here. So what you can do, you can actually consider say theoretical solutions of these equations. Consider solutions of equations 1 as, so you can write something like, how would you express the solutions? You will write theta 1 is equal to something, because the left hand side is mu1 prime, mu2 prime, mu k prime. So the solutions will be in terms of that only, isn't it? After solving, you will get that. So theta k is equal to some hk of mu1 prime, mu2 prime, mu k prime. So this solution system, let me call it to be 2. So in the method of moments, what we do, we simply replace this in the solution vector. I replace this mu1 prime, mu2 prime, mu k prime by their sample analogs. Okay. So in the method of moments, we replace mu1 prime, mu2 prime, mu k prime by the corresponding sample moments. So let me define sample moments. So for example, okay, I can use say some notations like alpha 1, etc. So the first sample moment, that is the sample mean, let me call it alpha 1. Alpha 2 is the second, that is I is equal to 1 to n, sigma xi square 1 by n, and so on. Alpha k is equal to 1 by n, sigma xi to the power k, I is equal to 1 to n. Okay. So I will replace in this solution here theta 1, it will become h1 alpha 1 alpha 2 alpha k. So this theta 1 theta 2 theta k I will call to be the estimates. Okay. So the method of moments estimators, which we will use abbreviation MMEs, okay, of theta 1 to theta k are given by theta I head is equal to hi alpha 1 alpha 2 alpha k, for I is equal to 1 to k. Let me start with some simple exercises. Suppose I have a random sample from a Poisson distribution. Okay. So the first moment is lambda. So lambda head will be equal to, I will write here lambda head MME, that is equal to mu1 head will be alpha 1, that is x bar. Okay. That is the method of moments estimator. Of course, here we have seen that x bar is unbiased and consistent estimator of let me take another example. Suppose I consider x1, x2, xn following normal mu sigma square. Okay. So if I am considering this, what is the first moment here? That is mu. And what is the second moment? That is mu square plus sigma square. So that means you are writing mu is equal to mu1 prime and sigma square is equal to mu2 prime minus mu1 prime square. So the method of moments estimators will be mu head MME, that will be x bar, and for sigma square it will be equal to alpha 2 minus x bar square, that is 1 by n sigma xi square minus x bar square, which I can also write as 1 by n sigma xi minus x bar square. We have actually studied the properties of this earlier in respect of unbiasedness and consistency. So x bar is seen to be unbiased and consistent for mu, and sigma head square MME, you have seen it is biased but consistent, because 1 by n minus 1 sigma xi minus x bar square was unbiased. So this is biased but consistent. So are these calculations clear to all of you?
Yes, sir.
Let us just do exercises for few more distributions. Suppose I consider this from exponential distribution. Okay. One parameter exponential distribution where lambda is the parameter here. So in this one, if I consider mu1 prime, the mean of exponential is lambda. So lambda head will become 1 by x bar. Okay. Again, we have seen this is not unbiased. Actually, we had derived in the last class the unbiased form of that is n minus 1 by n x bar. So this is different, which is biased and consistent. You can see here that if I am estimating 1 by lambda, then I will get unbiased as well as consistent. But if I am estimating lambda head, then the method of moments estimator gives me biased but consistent estimator. Okay. Is this exercise clear?
Yes, sir.
Okay, this problem will be it can have two parts, where n is known. If n is known, in binomial case, I don't have to write x1, x2, xn here because this is n here. So I have to modify a little bit here. I should put here x1, x2, xk. If n is known, then mu1 prime, that is equal to np, that gives you p is equal to mu1 prime by n. So p head will become equal to x bar by n. Okay, so here x bar is 1 by k sigma xi. Otherwise this n and this n will get confused here. So okay, so this is method of moments estimator of p. I'll consider more general case where both n and p are unknown. Okay, this kind of situation occurs in large sample trials where the trials may be considered to be Bernoullian, but we do not know at what point we will stop. So in general, n may be unknown. So for example, people reporting at a hospital for COVID, so then they are being tested for whether they have COVID or not. So if they have COVID, then it is P, otherwise, then it is 1, otherwise it is 0. But the number of people every day may be different. So n may be unknown in that case. If that is so, only thing is that outcome will be known, like I will know x1, x2, xk. That means how many of them have been observed to be positive. But out of how many, that will be varying all the time. So in that case, I may have to estimate both n and p. So I will have to write two equations. First one is mu1 prime is np, and then mu2 prime also I have to write, that is n square p square npq, that is np into 1 minus p. So let us write down the solution from here. This will give me actually, we can just use some small tricks here. So for example, mu2 prime minus mu1 prime square, that is np into 1 minus p. So now if I divide this by the first one, then I'll get 1 minus p as mu2 prime minus mu1 prime square divided by mu1 prime. So 1 minus that will give me p. So from here I will get p is equal to 1 minus mu2 prime minus mu1 prime square by mu1 prime, and n of course is then mu1 prime by p. So divided by this entire thing, which I can also write as mu1 prime square divided by mu1 prime minus mu2 prime minus mu1 prime square. Okay. So this is just a solution of this equation. You can check the method of calculation. That is not a very complicated thing. Just it's a class 6-7 exercise. Only the moments part you should know, which you have done in the probability theory course. So replacing mu1 prime and mu2 prime by alpha 1 and alpha 2, we get method of moments estimators of n and p as so let me put it n head. Okay. So here mu1 prime will be replaced by alpha 1, that is x bar. So that will give me x bar square divided by x bar minus, here this will be 1 by n sigma xi square minus x bar square. So I can club the two terms. It will become 1 by n is not there, 1 by k is there. So sigma xi minus x bar square. And for p, this will become that is x bar minus 1 by k sigma xi minus x bar square divided by x bar. So these are the method of moments estimators for n and p when both of them are unknown. In the assignment sheet that I will be giving, there will be a lot of problems on various distributions. For example, you can do for gamma distribution, you can do for uniform distribution, etc. So there can be many things. I'll discuss few more. First thing that you observe here, that sometimes the method of moments estimators is unbiased, sometimes it is not. In the problems that we have done, generally it is consistent, but again it is not a rule, sometimes it may not be. Okay, so that is also possible.
Sir,
yes.
can you explain why 100K need not be equal?
What need not be equal?
100K.
This is from binomial NP. So here I am taking n to be the parameter. So I should not take the same as the sample size. So that's why I have changed it to x1, x2, xk. Because this is binomial NP. So here n is the parameter, not the sample size. Okay. Is that clear?
Yes, sir.
Okay. They will be consistent if here the function that we have considered in the derivation here. So here you look at, I am replacing this mu1 prime, mu2 prime, mu k prime by alpha 1, alpha 2, alpha k. So they are the sample moments. We have seen that the sample moment is consistent for the corresponding population moment, provided the variance of that is finite. So here in general that will be true. Okay, whenever this moments exist. So mu1 prime, mu2 prime, mu k prime. So if the function h1, h2, hk, if they are continuous functions, then the consistency will be also true. Okay. If the condition for consistency of sample moments for corresponding population moments is satisfied and the functions hi's are continuous. Let me give one example which is slightly different. Let us consider, say, uniform distribution. Okay. Let x1, x2, xn be a random sample. from uniform distribution on the interval, say theta 1 to theta 2. So of course theta 1 has to be less than theta 2. Okay. So let us consider the moments here. Mu1 prime here is theta 1 plus theta 2 by 2. This we have done in the probability theory course, the moments of various distributions. So you have to just revise those things. The second moment is theta 1 square plus theta 2 square plus theta 1 theta 2 divided by 3. So you need to just solve this to get the values of theta 1 and theta 2. So theta 1 is equal to mu1 prime minus square root 3 mu2 prime minus mu1 prime square, and theta 2 will be same thing, mu1 prime plus first thing we notice here that the inside quantity, that is mu2 prime minus mu1 prime square, is variance. So this is always non-negative, so this square root is valid. So basically it is something like root 3 sigma limits. In the case of uniform distribution, in place of 3 sigma limits, you are getting the estimates as the minus root 3 sigma limits. Okay, so this is an interesting observation that you can have here. So the method of moments estimators will be so theta 1 head will become x bar minus square root 3, and I'll call it s star, and theta 2 head is equal to x bar plus root 3 s star, where I am defining s star as s star square is 1 by n sigma xi minus x bar square. Okay, so this is very interesting from a description point of view. Sometimes you may be faced with slightly unconventional situation. For example, you have k parameters, but when you write down the first k moments, then all the k parameters may not appear due to spatial structure of the distribution. In that case, you may have to write maybe k plus 1 moments. So I'll just give you one simple example. So I'll just give a very simple exercise from where it will be clear. So generally, if I have one parameter, I should write one moment. Okay, that is the mean. But let us consider this exercise where x1, x2, xn is a random sample from a uniform distribution on the interval minus theta to theta. Okay, so here if I consider mu1 prime, that is 0. So I will not get the estimator for theta from here. So I will have to then consider one more. So let me put mu2 prime, that is of course theta square by 3. So I will get the estimator of this from square root 3 mu2 prime. So theta head will become square root 3 by n sigma xi square. So this is the method of moments estimator here. Is this exercise clear to all of you?
Yes. Yes.
So in statistics, actually, apart from mathematical derivation, you have to also apply the statistical sense also. So here, because of the structure of the distribution, if we just take the mean, then it vanishes here. So therefore, we need some sort of extra thing here. So let me give you one exercise now. Let us take, say, x1, x2, xn follow gamma distribution with parameters, say, r and lambda. Okay, and second exercise I am giving you, x1, x2, xn follow beta distribution with parameters, say, alpha and beta. Okay. In both of these, you find out the method of moments estimators. Okay. Okay, now it is, I think, 5 minutes to 4. So let me give you some time to do that, and we can have a break also for 5 minutes. So I'm giving you total break for 10 minutes, and after that I will like to listen to you. What is the solution for method of moments estimators for R and lambda in the first problem and for alpha and beta in the second problem? Okay, so you please solve these two problems now. So let me hear the solutions. This Venkat Sai, do you have solutions now?
So for the first part, lambda hat and
Yeah, what is lambda head and what is R head?
so lambda hat is x bar by 1 by m sigma xi minus x bar whole square.
Right. And for
R
R?
hat x bar square by 1 by m sigma x minus x bar square.
Yeah. So in the first problem, here we have R head is equal to x bar square divided by s star square. S star I just now defined here. Okay, so I'm just writing the same notation here. And lambda head is equal to x bar divided by s star square. Other students are also able to get it. Let me ask any other person. Priyanshi. Okay. Now let me come to the second one. And let me ask who has solved it. Vishnu Vardhan, have you solved it?
No, sir, not yet.
Not yet. Abhibhu Prakash.
No, sir.
Okay, Anushka.
Still have to simplify it, sir.
Okay, please solve it. Okay, I am giving you another 2-3 minutes, and by that time you please solve it for the beta distribution. Okay, I am giving you another 3 minutes.
So for alpha, it is x bar times x bar minus x bar square minus s square by s square.
Hello, sir. Hello. Am I audible, sir? Hello. Hello, sir.
I would
Hello.
like to hear the solution now.
Yes, sir. I get answer, sir.
Yeah, please tell.
Sir, beta distribution, we get alpha equal to x bar multiply with summation of x I square divided by n minus x bar whole divided by h square. Variance, sir, sample variance. Okay,
X bar
and sir,
multiplied by
summation of xi square by n minus x bar and whole divided by h square.
this multiplied.
Yes,
I could
sir.
not hear. X bar
Sir,
minus
x bar minus x bar square
Next,
minus
sir,
s square.
summation of xi square.
Okay, let me just check with some other person also. Let me ask Priyanshu.
Sir, I am doing it.
Okay, anybody else can verify? Vijay Kumar.
Sir, it's x bar times x bar minus x bar square minus s square.
Okay, that
Which
is what I have written.
Yeah, the same thing as this.
Okay, fine. Okay, so I think it's okay. All right, I mean, I will give you some more problems, but that will be in the assignment. Let us move to the next method. This method is extremely, you can say, simple because it just involves evaluation of the moments. Of course, because here the parts of the distributions are standard, but if you are dealing with certain non-standard distributions, then evaluation of moments may be complicated, as well as the solution, because here you have to also solve the equation. So for example, in the alpha distribution, this beta distribution, or in the gamma distribution, etc., there is little bit complexity, but only it is 2-parameter problem. But if you have say more number of parameters, then things may be more complicated. And another thing is that it does not yield unbiased estimators most of the times, because nonlinear transformations are there. And consistency may be in problem if continuity of the solution function is not maintained. The problems that we have solved here, in fact, in all of them it is there. So it's a simple heuristic method, but it can be easily applied by anyone who knows little bit of knowledge of distribution theory. Okay. But later on, another method was proposed. It is called the method of maximum likelihood estimation. So it is typically attributed to R.A. Fisher. I had mentioned the names of these statisticians earlier. So around 1912 onwards, he developed this method, and finally in 1922 paper and 1925 paper, he has given the firm foundations of this. I will start with a simple exercise. Okay. So suppose we have a box with say black and white balls. Suppose they are identical type. Okay. Because if we have to choose, then we at least the size will not make any difference when you are taking out the balls, or it can be some marbles or some pebbles, etc. Okay. They are in the ratio 1:3 or 3:1. That means it is not known. That means either white balls are more, 3 times more than the black, or it could be the black balls are 3 times the white balls. That part is known, but it is not known which one is more. Okay, so based on a random sample of say 3 draws, so the proportion of basically black to white or white to black. Okay, so we want to know the true proportion. Let us not call this as P. Rather, we can call the probability of drawing as P. Okay, let P be the unknown proportion of say black balls in the box. So then P is either 1/4 or 3/4, but we don't know which one. So we want to estimate on the basis of 3 draws of the balls from the box. So if I consider X as the number of black balls drawn, then out of 3, you can have X is equal to 0, 1, 2, 3, and this will become actually a binomial distribution. In place of n, we have 3. Okay, where P is either 1/4 or 3/4. So let us consider, we want to estimate the value of P. Okay, so let us consider the probability that X is equal to K. So that is 3Ck P to the power K, 1 minus P to the power 3 minus K, where K can take values 0, 1, 2, 3, and P can take values 1/4 or 3/4. These are the all possibilities here. Okay. Let me represent these probabilities in the form of a table. Okay. Tabular form will be convenient to describe actually. Let us put say X here or K. So K is equal to 0, 1, 2, and 3. These are the possible values that K can take. And what is the value of probability for P is equal to 1/4 or 3/4? Okay. Let us just look at this. I have written the function here. If I take K equal to 0, I will get here 1 minus P to the power 3. Okay. So if I take P is equal to 1/4, then this will become 3/4 cube, that is 27/64. And if I take P is equal to 3/4, then 1 minus P to the power 3 will become 1/4 cube, that is 1/64. Similarly, if I take K equal to 1, then this is 3 times P into 1 minus P square. Okay, so if I take P is equal to 1/4, then this is 3 into 1/4 plus 1 minus 1/4 square. So that is 3/4 into 3/4 square, that is again 27/64. And if I take P is equal to 3/4, then I will get here 3 into 3 by 4 into 1 minus 3 by 4 square, that is 1 by 16. So it is 9 by 4 into 3 by 16, that is into 1 by 16. So that is equal to 9 by 64. Let us look at p equal to 2. For p equal to 2, this is 3 p square into 1 minus p. So if I take p is equal to 1 by 4, then this will become 3 into 1 by 4 square into 1 minus 1 by 4. So that is 3 by 4. So 9 by 64. And at p is equal to 3 by 4, this will become 3 into 3 by 4 square into 1 minus 3 by 4. So that is equal to 27 by 64. Finally, for k equal to 3, it is p cube here. So p cube will become 1 by 64 and 27 by 64. So this is actually probability of x is equal to k. I have written for various options. So the person who has done the experiment, he has 3 outcomes available to him. That means he has drawn 3 balls from the box, and out of that he knows how many black and white balls he is having. Like he may have 0 balls, 1 ball, 2 ball, 3 ball. On the basis of that, he has to conclude that whether I should take p is equal to 1 by 4 or 3 by 4. So what is a common sense logic? So you look at this. Suppose he gets out of 3 balls which he has drawn, none of them is black, all of them are white. So you can see here that if p is equal to 1 by 4, which is corresponding to less number of black balls, the probability of likelihood of no black balls appearing in 3 draws is higher compared to the probability when p would have been 3 by 4. That means if in fact in the box there were more black balls, then the likelihood of none of them being 0 is much smaller, that is 1 by 64. And if the black balls are actually less, then the probability of getting only 0 black balls out of 3 is much higher. So what is my guess? My guess would be that p should be taken to be 1 by 4. That means the one corresponding to the higher likelihood of this sample arising. Similarly, if you look at 1 again means that out of 3 drawing, only 1 black ball is there, 2 white balls are there. Here also you can see that p is equal to 1 by 4 gives you higher probability, whereas p is equal to 3 by 4 gives a smaller probability. On the other hand, if I am considering out of 3 balls, if 2 black or 3 black balls have been drawn, you can see that the probability of this is higher, corresponding to p is equal to 3 by 4. P is equal to 3 by 4 means that we have assumed that there is more black balls are there in the box corresponding to as corresponding to the white balls. So that means if there are more black balls in the box, then the probability of getting more in the sample is also higher. So a common sense logic suggests that, so we observe that the likelihood of, I am using a different terminology, likelihood I am calling it, p is equal to 1 by 4 is higher when k equal to 0 or 1, and that of p is equal to 3 by 4 is higher when k equal to 2 or 3. So we should take the estimator of p hat to be 1 by 4 if k equal to 0 or 1, and it is equal to 3 by 4 if k equal to 2 or 3. This is called maximum likelihood estimator. The previous one was called method of moments estimator. This is called maximum likelihood estimator because the likelihood of occurrence of a particular thing is higher when. So we are looking at the maximizing value. So if we formalize this concept, so what is likelihood function? It is nothing but the probability mass function here. Okay, but I am looking at for each value of k, which value of p gives you the maximum here. Okay, so in this case only two of them are there, so it is an easy comparison. Just from making a table I am able to do it. If only two values are not there, suppose I am saying p lies between 0 to 1, in that case it is a mathematical analysis problem because we know how to find out the maxima and minima of a function, so we can do that. So let me now give that thing. So this gives the method of maximum likelihood estimation. That is, if a sample x1, x2, xn is equal to say small x1, small x2, small xn is observed, then the joint probability mass function or probability density function of x1, x2, xn at the point x1, x2, xn is written as, so I am now writing down product p xi theta I is equal to 1 to n or it could be product f of xi theta I is equal to 1 to n, depending upon whether you have a probability mass function or you have a probability density function. So this is called likelihood function L theta x. Okay, so the joint probability density function of x1, x2, xn at the point x1, x2, xn is written as the likelihood function, and this function we maximize with respect to theta. So this is discrete case, this is continuous case here. So we maximize L theta with respect to theta, okay, over theta belonging to theta over the whole parameter space. Okay, so the maximizing value, that is theta hat is equal to theta hat, of course it will be dependent upon x1, x2, xn, is called maximum likelihood estimator of theta. Okay, so in general it is an analysis problem here. Okay, so is this method clear? Then I will solve some of the problems here. Is the method clear to you?
Yes, sir.
So let me start with some exercises here. Let me extend this exercise. This is binomial distribution problem. Let me extend this to, in place of 3, suppose I have n here, and p need not be just 1 by 4 and 3 by 4, but p can be any value between 0 and 1. Then how will you get the solution? So let us look at it. So many times you will observe that the solutions of the method of moments and maximum likelihood estimator will be same. in some cases they will lead to different solutions. So we will have different problems, and you can see the setups. In the different setups, different answers will come. It need not always be the same. So that is why it is a different method. But many times, of course, the solutions will coincide. So let us look at, say, X following binomial NP. So we have n Bernoullian trials in which P is the probability of success, and in each trial, and n is known here. Okay. So X is the number of success here that is having binomial distribution. The method of moments estimator for P here, you know, it is X by n. Let us look at the maximum likelihood estimator. If maximum likelihood estimator is to be derived here, then I will have to write down the probability mass function here. So the likelihood function so as I mentioned, I will use the notation L for the likelihood function. Okay, so this is nothing but the probability mass function of this distribution. So it is NCX p to the power x 1 minus p to the power n minus x, where x can take values 0, 1 to n, and p lies between 0 and 1. You try to understand the problem here. N is known here for different values of x. What is the value of p which maximizes this? So maxima minima problem, as in the calculus, you know how to solve it. Generally, if the function is nice, that means it is continuous and differentiable function. What we do, we look at the nature of the first derivative. We look at where it is increasing, where it is decreasing, and from there we determine the points of maxima and minima. So you can do it for this itself. The only difficulty here is that actually you have to differentiate with respect to p. And the term which is there, it is actually slightly complex because p to the power x and into 1 minus p to the power n minus x. So although you can do it, but it is slightly complicated. So what you can do, because you know that in differentiation, etc., if we actually have little complexity, then what we do, we simplify by taking logarithmic, etc. So if we take log of this here, the maximization problem does not change because log is a one-to-one function. It is actually an increasing function. So maximizing L px with respect to p is the same as maximizing log of LP with respect to p, as log is a continuous, in fact it is differentiable also, and differentiable increasing function. So the problem does not change. Okay, wherever you are getting the maximum for L, same where in the similar point you will get the maximum for log L also. So let us consider. So I'll give a slightly different notation. I'll use a small l. Okay, it is called actually the log likelihood. In statistics books, you will find this standard terminology. So log likelihood is log of LPX, that is equal to log of NCX plus x log p plus n minus x log of 1 minus p. Okay. So now this has become much simpler. So I will have to consider derivative of this with respect to p. So that is equal to x by p minus n minus x by 1 minus p, which you can write in a slightly nice form. X minus np divided by p into 1 minus p. So easily you can see that dl by dp it is greater than 0 if p is less than x by n, and it is less than 0 if p is greater than x by n. That means if I consider plotting of this LP function, then up to x by n it is increasing and then it is decreasing. At p is equal to x by n, because for p less than x by n it is positive, the derivative is positive, so it is increasing, and then thereafter it is decreasing. So the maximum is attained at p is equal to, so max value of LP is attained at p equal to x by n. Is that clear?
Yes, sir.
So P head ML is actually x by n, the maximum likelihood estimator, which is of course unbiased and consistent, that we have already seen. And here it is the same as the method of moments estimator in this particular problem. Okay. But this is obtained in a different way because we are looking at the likelihood and we are trying to see that when it is maximized. Okay. So the idea behind the method of moments and the method of maximum likelihood is different. In the method of moments is simply a direct, you can say, mathematical technique which just equates the sample moments to the population moments, and from there we just solve the equations to get the estimators for the parameters. So that is just like a mathematical formula. Whereas the method of maximum likelihood is based on certain principle. What is the principle? The principle is that we are looking at the likelihood of a particular sample arising out of a population with certain parameter. So when that likelihood is maximized at a particular parametric configuration, that means which sample gives the maximum probability of occurrence. Okay. So it has a certain principle, basic principle is there. That is why this method has gone lot of popularity, although it was obtained about 100 years back in 1912 onwards. So now it is 2022. So actually in 1922, the major paper of R.A. Fisher was published where he elaborated and this method and its properties. But if you consider any applications in different areas of science and technology, wherever the data is occurring, then in order to consider estimation of the parameters, this method is the most used method actually. So let us look at some other problems. So for example, yeah.
So in this example, how did we come up with the likelihood that function L?
So as I mentioned, what is the likelihood function? Likelihood function is called, if you write down the probability mass function, in the probability mass function, x is the variable and p is the parameter. So we consider p as the fixed value. When we call it likelihood function, the same thing, then here x is observed here. So p is the unknown thing which we want to estimate. So the name is changed here. The probability mass function or the probability density function is considered as a function of the variable and parameter is fixed. Here the sample has been taken, so x is fixed now and p is the thing which we want to determine based on that. So the likelihood function is nothing but the probability density or probability mass function with a new nomenclature. Okay, the nomenclature is that now you have to consider it as a function of p and consider the maximization with respect to that. Is that clear?
Yes, sir. Thank you.
So can it be applied for like more than one parameters?
Yes, yes. I wrote the general method, no? So here what I have written? I have written the joint distribution of x1, x2, xn, and here theta could be a vector parameter. Okay. But you have to then apply the method of maximization for the several variables. I hope you have done that in your maths courses. Are you aware of that? The maxima minima of function of say 2 variables, etc. Have you done that?
Yes, sir.
Yeah, so let me solve some more problems because this method you should try to understand properly.
So here, what is X? P capital X.
What is your question? I cannot hear. Tell me clearly.
So here P hat ML equal to capital X by M, right?
Yeah.
I did not get that X. What is that X?
So we got the data here, no? This X. X is the
Yes.
binomial distribution. So we want to estimate the population proportion P. So method of maximum likelihood gives the sample proportion as the estimator. This is sample proportion. So suppose we want to estimate say COVID positivity rate in a particular place. Okay. So how would I do that? I will test some people. For example, there is a prevalence in say M hall. So from M, we are not going to test everyone, but certain number of students are selected and they are tested. And out of that, suppose we find, say 50 students are tested, and out of that, say 10 students are positive. So we will say the positivity rate is 0.2. Okay, but everybody has not been tested. So it is a sample estimate of the population proportion. Is that clear?
So sir, here X will be 10.
10?
The example you said.
Yeah. X is 10, N is 50.
Okay.
So suppose I have a random sample from Poisson. Okay. So I'm using the small x1, x2, xn here. So the likelihood function is so Poisson distribution probability mass function, you know, e to the power minus lambda, lambda to the power xi by xi factorial. Okay. So let us write it in a slightly simplified form. Once again, you have to consider maximization with respect to lambda here, and lambda is appearing once in exponent, another time here in the base. So this is slightly complicated, and also there is a product of the terms. So if I consider the log likelihood, the terms will become simple. So that is equal to minus n lambda plus sigma xi log lambda minus log of product xi factorial. So if I consider first derivative, that is minus n plus sigma xi by lambda, which I can write in a slightly nice form as n times x bar minus lambda by lambda. So again, you can see here that this is positive if lambda is less than x bar, and it is negative if lambda is greater than x bar. So if I plot this function, that is L of lambda, then you can see that it is increasing up to x bar and then it is decreasing. So there is a maximum at this point. Okay. So L is maximized at lambda is equal to x bar. So the maximum likelihood estimator of lambda is x bar here. So are the calculations clear to you?
Yes.
Maybe I think today's time is almost over here, so I will not increase the time here for another problem. So I will now this weekend, because now we have covered many topics, so I will be able to give one assignment here based on unbiasedness, consistency, the method of movements, and maximum likelihood estimation. So you please solve those problems. Okay, you need to solve those problems, otherwise you will not understand the concept here. So I will stop today's class at this point.
Sir.